All right, in this section, we'll talk about reactions of alkanols. Alkanols are acidic in behavior due to the presence of the hydroxyl group, the OH group. In the presence of active metals such as sodium, potassium, and magnesium, the hydrogen on that hydroxyl group can be easily removed with the formation of an alk oxide. Alkanol is first mixed with a pinch of anhydrous calcium sulfate. The purpose of that is to remove the water, because water is also highly reactive with sodium metal, and it therefore has to be removed first completely. Once that clear solution is decanted, we can add a small piece of, say, sodium metal to the alkanol. There will be a brisk effervescence. We'll see bubbles and formation of gas due to the formation of that hydrogen gas, indicative of an alkanol functional group. So, as an example here, I have methanol and ethanol as my starting materials in these two separate reactions. When we add a small piece of sodium metal, we end up with this. The sodium now has replaced our hydrogen, and we have the formation of this hydrogen gas H2, okay? So the primary alcohol, CH3OH, is more acidic and reacts faster, so its reactivity is the greatest. As more carbon groups are added to forming the secondary and tertiary alcohols, they are electron donors. The oxygen atom is more negative and less stable, resulting in a lower reactivity. So primary alcohols are more reactive than secondary alcohols, are more reactive than tertiary alcohols. The next reaction we'll talk about is the dehydration of alkanols. Alkanols can be dehydrated to produce alkenes by heating while passing the vapors over heated catalysts such as aluminum oxide or zinc chloride. So here's an example. Here's an alkanol, our OH group. As we heat it, so really high temperatures here, it will vaporize. And if we pass those vapors over a catalyst of aluminum oxide, we can dehydrate. Remember, dehydrate would be to remove a hydrate group, a water group, and form an alkene. So the alkene would be the double bond between these two carbons. It would mean the removal of this OH group and the removal of one hydrogen here in the formation of that double bond. So we end up with a double bonded alkene and water. Another method of producing alkenes through dehydration of alkanols involves heating the alkanols with concentrated H2SO4 or H3PO4 at temperatures above 400 Kelvin. So we can dehydrate. This is the same reaction that we saw in the last slide. So we just end up with a double bond. And then in this case, so remember in this case that this means that the OH group is bonded to the preceding carbon. So we're bonded to this carbon here. And then we end up with the formation of a double bond between this carbon and the neighboring carbon. This reaction, and of course we would have the formation of water here. We're not showing it, but remember this is dehydration, so these should all say plus water. We're just showing the location of the double bond, okay? This reaction can also take place in the reverse direction. So if I go the reverse direction with cold H2SO4, I can rehydrate that alkene back to an alkanol. So let's talk about that hydration of alkenes. Indirect hydration of alkenes in the reverse direction with cold H2SO4 produces alkanols. It proceeds with the addition of water across the double bond to produce the alkanol. The relative ease of dehydration enables the following reaction path. So tertiary alcohols are easier to dehydrate than secondary, are easier to dehydrate than primary alkanols. Here are some examples of dehydration reactions involving alkanols. So we have a primary alkanol here, a secondary alkanol here, and a tertiary alkanol here. In this case, the temperatures are all constant, 440 Kelvin, but we have 95% H2SO4 in the case of the primary alkanol to dehydrate and form the alkene. Here, 60% H2SO4, and here, 30%. So this clearly indicates that reactivity of these tertiary alkanols is greater than secondary, is greater than primary, because we don't need as strong of an acid in order to drive this reaction forward. Let's now discuss mineral acid reactions with alkanols. Mineral acids like concentrated HCl, HBr, etc. can break up the carbon OH group bond, resulting in the formation of what are called alkyl halides. The OH group will be replaced by the halogen atom. So as an example, we have some alkyl group CH2OH plus our mineral acid. So here's an example. We have ethanol here and HCl. And the product will be water from the OH group and this hydrogen. And now whatever this halogen is will be attached on this end where the hydroxyl group was for an alkyl halide. So in this case, instead of ethanol, we have this ethyl chloride and water. The reactivity of alkanols increases from primary to secondary to tertiary in the case of mineral acid reactions with alkanols. Alkanols can also be oxidized. Primary alkanols are oxidized to alkanoic acids by oxidizing agents like acidified KMnO4, potassium permanganate. So we have alkanol and this oxidizing agent, and a product is the alkanoic acid. So remember, this is a C double bonded to an O and then single bonded to an OH group, and our product is hydrogen. If CrO3 is the oxidizing agent, so you can see that in all three of these cases here, we have more control of the reaction and can cover the first stage oxidation product, can recover the first stage oxidation product as an alkanal. So there's a way to control this reaction where instead of producing an alkanoic acid, we can just have this C double bond O single bond H on this terminal carbon in this case. So we have this carbonyl group without the hydroxyl group. So just an alkanal as our product. So this is similar to the previous slide, but with a different oxidizing agent. We can stop the reaction at this point and have C double bond O single bond H as an alkanal instead of an alkanoic acid. And then of course hydrogen as well. Alkanols can also form sweet smelling compounds called alkanoates. They're also known as esters when heated with a carboxylic acid in the presence of a strong acid. And so what we have here is our alkanol. Here is our carboxylic acid or our alkanoic acid. Okay. And then look at what happens here. We have this combination. This portion from the carboxylic acid, okay, combined with the alkyl portion of the alkanol, and that leaves us with an OH here and an H here, which form water. Okay? So an alkanol and an alkanoic acid can combine to form what's called an alkanoate, or an ester. And they have a characteristic sweet smell to them. Esters are used for a lot of artificial fragrance, like banana fragrance and other fragrances. And so there are several examples shown here, but they all can be similarly shown. This portion of the alcohol, right? All right. Combined with, so let's see, there we go. Combined with the carboxylic acid. So here, so you can see them all. And then, of course, water as a product.